So it's our pleasure to have Vidya Madhavan from University of Illinois at Urbana-Champaign. Vidya did her graduate work under the tutelage of Seamus Davis at Cornell University, and then did her postdoc at Berkeley, working with Michael Cromie. She started her faculty position at Boston College, and she worked on a variety of correlated materials, superconductors, and topological insulators. The group of papers that had the most effect on the research that I actually do here involved really elucidating a lot of the interesting aspects of a topological state called a topological crystalline insulator. Today's work is, I'm really excited to hear, it's very substantial research into a new superconductor, an iron-based superconductor comprising of elements of iron, selenium, and tellurium. A few years ago, this material was discovered to be both superconducting and topological. And once that was done, the race was off to determine whether Majorana fermions were actually excitations in the system. Vidya's work today will show us what she's demonstrated in the system. I think it's very important advancement in this particular field. And so I look forward to hearing to what she has to say. So Vidya, with that, take it away and let us know what you're up to.
Thanks, Jimmy. Just a quick thing. I was a graduate student at Boston University with Mike Cromie and did a postdoc with Seamus Davis, just to get the record straight. Okay, let me just start now. I'll share my screen. It works. Does it work?
Yes, beautiful.
Okay, good. Thank you. All right. So thanks, Jimmy. Yes, today I'm going to be talking about a couple of two different classes of materials, actually, where we believe we can see signatures of propagating Majorana fermions. And I'll explain what I mean by that. And the tool of choice for us is scanning tunneling spectroscopy. So let me just jump right into it. If my computer will allow me. Just one second, I'm having technical issues.
Is that a Majorana mode that we see before us?
Yeah, this is a lovely rendering by one of my colleagues, Emily Edwards. But hang on for 1 second. I don't know what's going on.
We know Emily very well. She did a lot of great scientific illustration work for us.
We're familiar with her quality work.
I know.
When she was here.
I am in. See, you can hear that. Okay, maybe it's working now. Let's see. Close this. Doesn't seem to want to work. Escape. I'm going to try again. This is the first time I've had any difficulties. Oh, there we go. Okay, good. All right. Phew. I was getting worried there for a second. I hope you can see my mouse now. You can, right? Yes. Okay. Okay. So let me just start. I like to think of topological superconductivity by making an analogy with ordinary topological insulators. And I just want to mention, you can have edge states or surface states, depending upon the dimensionality of the crystal, even in regular materials. For example, if you take a chunk of gold or copper or silver, and you look on certain facets, then we know for a long time, we've known for a long time that you can get these two-dimensional gas of electrons that live on these surfaces. And these are just ordinary surface states that exist on the surfaces of many materials. The thing about these surface states is you have electrons of all spins going in both directions. So that means that any ordinary impurity can scatter you from one direction to the other direction. Now, if you come to a quantum spin Hall insulator, which is a two-dimensional topological insulator, then you have very special edge modes. And in these quantum spin Hall systems, you have spin momentum locking, where an electron going in a certain direction must have a very well-defined spin. And now you get into a situation where ordinary spin-less impurities cannot scatter you from one spin channel to the other. However, magnetic impurities can create these scattering processes. And finally, you can have quantum anomalous Hall systems where you have these kinds of chiral edge modes. This is also a topologically non-trivial material. And in these quantum anomalous Hall systems, you have only one channel propagating around the edges with a well-defined spin. And now scattering processes are completely disallowed. And in fact, there's a huge race on to find a quantum anomalous Hall system that can have these propagating modes at room temperature. So these might be useful for electronics. So one important thing about all of these topological insulators or topologically non-trivial materials is that there's something called bulk boundary correspondence. And that means that the topology of the bulk dictates the kinds of edge states you would have. Meaning in this case, for example, you'll have helical edge states. And in this case, the topology dictates that you should have chiral edge states. So something similar it happens in the case of a topological superconductor. In a topological superconductor also, the topology of the bulk dictates the existence of edge states. For example, you can have a two-dimensional topological superconductor with one-dimensional edge modes, which are chiral, circulating around the boundaries of the system. You can also have a topological insulator where you have a superconductor where you have helical edge modes, just like in a topological insulator. And you can also have a bulk topological superconductor in 3 dimensions where you have very interesting surface states. Now, the thing about a topological superconductor is that it's a fundamentally new phase of matter in the following sense. Just like in order to go from a topological insulator to a trivial insulator, you have to go through a phase transition where you close and open the insulating gap of the topological insulator. Very similarly, a topological superconductor is a distinct phase from an ordinary superconductor. And in order to go from a topological superconductor to an ordinary superconductor, you must close and open a gap. So one interesting thing about topological superconductors that many people are interested in because of quantum computation is that the edge modes in topological superconductors are actually composed of Majorana excitations. So when you have these helical edge states, these are actually helical Majorana fermions that are propagating around the edges. And when you have these chiral edge modes in these particular topological superconductors, they're chiral Majorana fermions propagating around the edges. So this makes topological superconductors very interesting, both from a perspective of fundamental physics, but also from the perspective of applications.
So I've heard this topological superconductivity discussed before. And are you telling us that the view is that a topological superconductivity would always result in Majorana type particles?
Yes.
Or Majorana excitations?
Yes. So if you have a chiral topological, if you have a chiral triplet superconductor, which is topological, then its natural excitations are actually Majorana fermions. And I'll show you that in a second.
Thank you.
So just to answer your question, so what are the required ingredients for realizing Majorana fermions in a solid? So the definition of a Majorana fermion is that at 0 energy, when E equals 0, the particle is its own antiparticle. So the creation operator and the annihilation operator are identical at 0 energy. Now, Majorana fermions can exist at other energies as well. And the condition there is that the creation operator at a particular energy E must be equal to the annihilation operator at the energy minus E. So that's the condition for a Majorana fermion. So you can see immediately that because the states at E and minus E should be the same, you want to have particle-hole symmetry, And then that immediately takes you to a superconductor. So let's just look at a regular superconductor. The excitations of a normal superconductor are Bogoliubov quasiparticles, which are superpositions of particles and holes. And so these are creation and annihilation operators for Bogoliubov quasiparticles. You can see here that this contains both particles and holes with some weights given by UK and VK. Now, if you want to set these two to be equal, right, the condition for a Majorana fermion, let's see what happens. If you want to set these two to be equal, then the left-hand side and right-hand side should be the same. And that means automatically that UK equals VK, which is the amount of particles and holes in these Majorana excitations should be the same. So you can do that in a superconductor. That's not a huge problem. However, even if the amount of particles and holes are the same in a superconductor, so you have perfect particle-hole symmetry, you still have a problem in a regular superconductor. And the problem is that the left-hand side here has a spin-down operator, and the right-hand side has a spin-up operator, meaning that spins are flipped. So in a normal S-wave superconductor, you can't easily have Majorana fermions because of this problem of the spins being flipped. So how do you get Majorana excitations? One way is to eliminate spin as a separate degree of freedom. So if you could simply get rid of these spin degrees of freedom, and you can do this in many different ways, then you can have Majorana excitations as quasiparticle excitations of a superconductor. So let's just see how we can do that. So I'm going to talk about 3 different ways you can achieve Majorana fermions. One is that you can use a spin triplet p-wave superconductor. So usual singlet superconductors have up-down pairing, but you can also have triplet superconductors where you have pairing of electrons of the same spin species. And if you have such superconductors, then you can imagine that spin is no longer an important quantum number because the pairing is between the same spin species, and the excitations of a triplet p-wave superconductor could be Majorana modes. The problem with this, of course, is that there are very few known chiral triplet p-wave superconductors, and one candidate is uranium ditelluride. And what I hope to do today is, if I can get through the iron selenium tellurium, I want to tell you a little bit about uranium ditelluride. The other way to eliminate spin as a separate degree of freedom is by engineering the band structure of the system. So here's an engineered system. Let's say you have a semiconductor with very, very strong spin-orbit coupling. Then the regular bands, which are usually spin degenerate, get split in this way by spin-orbit coupling. Now let's just look at the dotted lines. That's what Rashba does to you. It splits the bands in this fashion. And now let's turn on a magnetic field or have magnetic impurities such that at the crossing point, you develop a gap. So typically this is done for these semiconducting wires by turning on a small magnetic field. And then you want to place, by gating or some other technique, you want to place your Fermi energy in this magnetic gap. And then you want to proximatize the system with a superconductor. So if you are able to engineer such a system, then you can see immediately that because of the band structure of the system, this band here, which is crossing the Fermi energy, first there's only one band crossing the Fermi energy. And the second is, due to strong spin-orbit coupling, the spin of the moment of each electron is locked to its momentum. So you've naturally eliminated spin just as a separate degree of freedom. And you can basically describe the superconductor just by looking at the at momentum space. So this is another way to engineer a superconductor where the excitations of the system could be Majorana fermions. And in fact, in the presence of a magnetic field, you can show that at the ends of the semiconductor wire, you expect to see Majorana bound states. The other possibility is that you can use topological insulators. I mentioned this before, but a topological insulator is a material where the non-trivial topology of the bulk, dictates the existence of very special boundary states. So for the case of a 3D topological insulator, you expect to have these very special two-dimensional surface states living on the surfaces of the system. The interesting thing about these surface states is that the dispersion is linear, close to the Dirac point, and also that the electrons have the same property that I mentioned before, which is spin momentum locking. So if you could take a topological insulator and if you could proximatize it with a superconductor, then you can achieve a situation where the excitations are Majorana fermions. So
Vidya?
Yes.
1 second. There's a question from the YouTube stream from Adam W. It's a little belated, I guess. Sorry for my delay. So the question is, would you expect Majorana modes in an excitonic condensate where particle and hole quality is always equal? I'm assuming it means whole quantity is always equal, but I'm not sure.
Sure. But you have to satisfy all of these other conditions as well. So you need equal, weights of particles and holes, but you also want to eliminate. So usually you have, at any given energy, you have a spin up electron and a spin down electron. You want to eliminate one of those electrons. And you have to sort of take a lot of trouble to do that. Like in a topological insulator, you get it for free because you have only one spin species at a given energy. Just to compare that with a Rashba spin split system where you always have two spin species. You can see that here. So yes, if you have an excitonic material and you can sort of bring yourself into, this kind of a situation, right? Then you can have Majorana excitations.
Thank you.
Okay, so Liang Fu and Charlie Kane proposed in 2008 that if you take a topological insulator and proximatize the surface states of a topological insulator, but with a superconductor, then there are two circumstances where you can get Majorana modes. One is you can get Majorana bound states inside vortex cores. So what you do is you turn on a magnetic field. And when you have a magnetic field, then you get these vortices, which are localized objects. And in the core of the vortex, you can see these Majorana bound states. By bound states, I mean that the Majorana state exists as zero energy and is localized in real space. However, you can also do something different. If you could have two superconductors with a pi phase shift between them, then they also showed that at the boundary between these pi phase shifted superconductors, you would see dispersing Majorana states, meaning propagating Majorana. These would propagate along the boundary, but these would be helical Majorana modes. So there are many ways of realizing Majorana modes. So the two things I hope to tell you about today are this kind of proximitized topological insulator, where you can see both Majorana bound states in the vortex core. So these exist only at zero energy. Or you can see helical propagating Majorana modes at these pi phase shifted boundaries between two superconducting states. And I also want to, if time permits, talk about this new compound called uranium ditelluride, which is thought to be a triplet P-wave superconductor. That was the thing that I first mentioned. And in this case, you would expect to see chiral. This system, if this is truly a topological superconductor, should break time reversal symmetry. And instead of having two branches like this, you should have only one branch of propagating Majorana modes at the boundaries. And so for this system, you expect to see chiral Majorana modes. Okay, so let me just start with this proximitized topological insulator. These are the people who did the work on this system. We had really beautiful single crystals from Genda Gu at Brookhaven. We had a bunch of theory help, both from Taylor Hughes here at UIUC and Dirk Moore at the University of Illinois, Chicago. And the STM studies were done by my former postdoc, Zhenyu Wang, and my current graduate student, George Rodriguez. Okay. So first, very quickly, I want to mention that I'm pretty slow here. I should mention that the reason you expect to see Majorana bound states and helical Majorana modes in these proximatized topological insulators is that they're actually time reversal invariant examples of spinless px plus ip bias superconductors. And so I've been telling you before that triplet superconductors have Majorana excitations quite naturally. So what you can show, and that's what Fu and Kane showed, is that these proximatized TIs behave exactly like these triplet superconductors, except they're time reversal invariant versions. So you can see that very easily. You can read the paper. It's actually a very beautiful paper. And I just want to hint at this for a second. So what you can do is you can take a Hamiltonian, which is the Hamiltonian of a topological insulator with Dirac surface states. So this is Dirac dispersion, right? And then you add a superconducting pairing just by adding this term to the Hamiltonian. And if you do that, the resultant Hamiltonian looks like this. And all you do to see that this looks like a spinless p plus ip superconductor is that you just redefine new operators and write the Hamiltonian in this new basis. And if you just transform the Hamiltonian using this new basis, you'll see that the projected Hamiltonian looks like this. And this term is exactly the kind of pairing you get for a triplet superconductor. So this is the reason that in these proximatized topological insulators, you see Majorana fermions, just like you see Majorana fermions in triplet superconductors. So the problem for many years for STM people, transport people didn't have a problem with this, but for STM people, you can think of this geometry. It's really tricky. You need a topological insulator, you need a superconductor, and then you need to sort of be able to tunnel into the system, and you need to make sure that the surface is clean and so on. So this geometry has been very difficult for us to achieve. However, in about, when was this? This was 2015. It was shown that this system, iron selenium tellurium, might be an example of an intrinsic proximatized superconductor. So by intrinsic, I mean that we've known for many, many years that this material, iron selenium tellurium, is a superconductor. However, what was shown in 2015 is that one of the bands of this material show band inversion. And band inversion is what you need to make the material topologically non-trivial. So if you have band inversion for just one of the bands at the gamma point, then what you expect is that you should expect these Dirac surface states. So you should see these Dirac surface states on the surface of this material. And since the bulk is known to be an S-wave superconductor, if it's a naturally proximatized system, so then you expect that for this system, you should be able to see Majorana modes inside the vortex cores and so on. So the phase diagram of FESCT looks like this. One end member is actually a spin density wave state. The other side is a superconductor. And it is for this very sort of a narrow range of compositions close to 50-50. I'm not sure how broad this is, but for this composition close to 50-50, you should see band inversion, and this material should be topologically non-trivial. So the band structure of the material looks like this. This is the Brillouin zone. You have a few different pockets. You have these alpha, beta, and gamma pockets at different parts of the Brillouin zone. And if you look at the gamma point, you have multiple bands crossing the Fermi energy, but the band inversion occurs between these two bands. So as a result of this band inversion, like I said, there should be surface states inside the gap. And in fact, ARPES studies showed the existence of these linearly dispersing surface states in this gap, right at this energy, close to the Fermi energy, you have linearly dispersing surface states. And so this is an ideal system to which all in one system, you have a proximatized topological. It's not an insulator; it's a metal, but you have a proximatized topologically non-trivial system. So we decided to look at this system with scanning tunneling microscopy. We have a few different STMs in my group, and the STM that we use to do these studies is a commercial system from Unisoku in Japan. It goes down to 300 millikelvin and it has 11 Tesla field. Okay, so what do you expect to see when you do STM imaging on the system? Well, the material is very layered and it cleaves very nicely. So it would cleave between these iron, selenium, tellurium trilayers. So it would cleave right here. These top atoms are tellurium. So what you expect to see is just these top atoms, which form a square lattice. So this is the top view. And these orange round circles represent the square lattice made by the top tellurium atoms. Notice that you also have tellurium atoms at the bottom, but they're slightly shifted. So these other orange atoms are the bottom tellurium atoms. And this shift is going to be important when we look for propagating Majorana fermions in the system. So if you look at a large scale topography, if you have nice crystals, then the topography looks like this. You can zoom in and you can see a square lattice. And all of this inhomogeneity comes from the fact that this is an alloy and almost a 50-50 selenium-tellurium substituted alloy. So the dark and the bright represent selenium and tellurium atoms.
Oh, excuse me, we have another question from YouTube.
Yes, sure.
I'm probably going to mispronounce the name, so sorry for that. From Tomagenberg. Oh, he just retracted his message, so.
Okay.
Sorry,
All
please
right.
continue.
Sure. So if you take, if you measure.
Could I ask you a question?
Sure, absolutely.
Sorry, this is Bill Phillips. Going back to your previous, yes, that slide.
Mm-hmm.
So now, should we understand that the selenium and the tellurium are essentially randomly distributed?
Correct.
In this, okay.
Correct.
Yeah. So right. So there's no ordering.
No, unfortunately, and that creates a lot of inhomogeneity. You'll see that in a second.
And does that apply throughout the entire phase diagram? I mean, from
yes.
Okay, thanks.
So there, as far as I know, there is no ordered phase of selenium tellurium. Sometimes you get that, but in this case, I don't think there is any.
Okay.
It's always a random alloy.
Hi, Vidya.
Yes.
This is Jay. So it looks like some clustering. Is that just a visual optical
it's
illusion,
visual.
or?
Okay. I mean, I don't know if it's visual or not. Okay, so you're right. You're right. I mean, this looks like, you know, there are regions of pure selenium and pure tellurium, but the band structure does evolve continuously when you go from one side to the other side. Mm-hmm. So. It doesn't say the length scale of this clustering is not, it seems like for the band structure, it averages over all this clustering. That's what it looks like. Okay. But there's certainly inhomogeneity because of this in the electronic structure.
Okay, but following up on Jay's question, it seems to me that to answer Jay's question as to whether there's really clustering, you could reasonably well answer it by doing something like a pair correlation function. You could find out whether this is Poissonianly distributed, or if there is the statistics of this seems like it should be something that that wouldn't be so hard to calculate and answer Jay's question explicitly. Sure.
We just haven't done it because it wasn't relevant to the physics that we were pursuing. Sure. But yeah, if you're interested in it, the inhomogeneity by itself, yeah, you could do that.
Okay.
Okay, so what do you expect to see? We measure density of states by measuring the differential conductance, dI/dV. So for an S-wave, this is an S-wave superconductor. For an S-wave superconductor, what you expect is coherence peaks and then the density of states going to 0. And so the position of the coherence peak tells you the value of the gap. So that's what you expect to see. So If you were to march along this line and obtain a spectrum at equal intervals, then this is what you get. So let's just focus on the first spectrum here. You can see the density of states does go to 0. I mean, this is 0, and these others have been offset, but the first one is not. So you can see that you have 0 density of states, like you would expect in an S-wave superconductor. You have these coherence peaks, which are particle hole symmetrics. They tell you the magnitude of a gap. However, as you march along, you can see many coherence peaks. In fact, if you look at this spectrum, you have 1, 2, 3 coherence peaks existing simultaneously. And the reason for this, having these many coherence peaks, is the fact that you have these many pockets that cross the Fermi energy. And as it turns out in this particular compound, each of these pockets actually has a different gap magnitude. So that's what you see in STM. So we can do it's pretty easy for us to do a statistical analysis and pick up all of these gaps and look at their histogram. And in fact, that's what we did. So we have, let's look at this last histogram here. You see 3 distinct gaps with the STM. And the mean gap values we get are these 1.3, 1.8, and 2.5 MeV. And if you compare that with ARPAS, we can identify the 1.3 millivolt gap with the gap for this alpha band, alpha pocket, for the 1.8 millivolt gap with the gap for the topological surface state that I was telling you about earlier, and the 2.4 millivolt gap with the beta band, beta pocket gap. So we can see all of these different gaps from the different pockets. So then the first, yes?
Sorry, Jay, this is Jay again. So if we go back one more slide, the spectrum data that you were showing, like here. So some of those peaks. So do those peaks appear to be moving with position? Like so,
yes.
Right. So that means that there's some kind of position dependence or composition dependence to this gap.
Yeah, so we haven't quite been able to correlate the actual gap magnitude variation with the density of any selenium or tellurium. There's no direct correlation, but definitely there's a lot of electronic inhomogeneity, just like in the cuprates. And that's why there's this, let's just look at this histogram. Even for the small gap, which is 1.3 millivolts, it's not exactly 1.3 millivolts everywhere. There's a range of gap values that you get.
I see. Thanks. Yeah.
Yeah. So now what do you expect when you turn on a magnetic field? Like I said, in such a system, which is proximatized, a topologically non-trivial proximatized system, if you turn on a magnetic field, in the vortex cores, you should see a sharp peak right at the Fermi energy. And this would be your Majorana bound state. And so, here's a map of the vortices when you turn on a magnetic field. So this is almost hexagonal. It's not perfect, but it's almost hexagonal. These dots that you see, they're actually not noise. These vortices, they want to move a little bit, just a tiny bit. And so all the dots and the streaks that you're seeing in this vortex map are the fact that the vortices want to move a little bit. In any case, if you go to one of these vortices and take a line cut, so far away you see a nice superconducting gap, and as you go through the center of the vortex, you see a very sharp peak in the density of states, which is centered at 0 bias. So in fact, this peak in the density of states was discovered not by us, but by another group from China, Hong Ding and his collaborators, in 2018. And what they found then, which was really interesting, is that not all of these vortices show 0 bias states. And in fact, only 30% of the vortices show 0 bias states. So this was a huge mystery at that time. Why don't all the vortices show these Majorana bound states? And in fact, later on, there's been a lot of work by Hanaguri's group and other groups that have shown under what circumstances you should see these Majorana bound states. And it turns out, I think, that at higher fields, as you increase the field, the number of vortices showing the Majorana bound states actually goes down dramatically. So at lower fields, you see more vortices showing these zero bias peaks. One thing I must mention that I'm not going to dwell on is that we always get bound states inside a vortex core. And those bound states, we've known this for a long time. These are just the normal Cayley-Metricon-Dejean bound states. The point about those bound states is that there is no reason for them to be at zero bias. However, depending upon the position of the Fermi energy with respect to the bottom of the band, the spacing between these normal, regular Cayley-Metricon states could be so small, they could be so clustered together that it seems as though they're right at zero bias in a particle hole symmetric fashion. So to distinguish that from a Majorana bound state, a lot of these, these people, this group and a lot of other groups have done a lot of work to show that these things are centered at zero and they can be well distinguished from the Cayley-Metricon Dejean bound states that you expect for the system. In any case, so when we saw this, we were very interested in knowing if you could also achieve propagating Majorana modes. So let me just remind you, if you have a pi phase shifted superconductor in proximity with a topological insulator, then at the boundary, you expect to see these propagating Majorana fermions. So let's ask, what do you need to see these propagating Majorana fermions? You need superconductivity. You need the material to be topologically non-trivial, that we have these. But then the question is, how do you get this pi phase shift? And this is an amazing material. It turns out that there is a nice crystallographic way to get a pi phase shift in iron selenium tellurium. And this work was done by Jianping Hu in 2013. And he showed that for many of these Nick-tight superconductors, you can consider, if you do a theoretical study where you consider both nearest neighbor and next nearest neighbor pairing, then you can show that there is sort of a parity shift between the top and the bottom layers of this material. So the interesting thing about this compound is, like I was mentioning before, that these are the top selenium/tellurium atoms. These are the bottom ones. They're shifted from each other by half a unit cell. So when the crystal forms like this, it actually picks that these would be at the top and these would be at the bottom, because you can imagine that the crystal could have also formed with these being, the top selenium atoms being here and the bottom selenium atoms being here. For this reason, because there are these two possibilities, you can imagine that in a normal crystal growth process, you might have regions of this phase, and then you might have regions where the crystal is phase shifted just a tiny bit in terms of where the top and the bottom selenium atoms are. So if you can find those kinds of regions where you have this shift in the selenium atoms, this is a half unit cell shift, then according to this theory at least, you should see a pi phase shift in the superconducting autoparameter. So let's just look for these kinds of domain walls and see what we find at the domain walls. So this is a pretty large area for STM. It's 100 nanometers, and there are no domain walls in this field of view. But actually, as it turns out, if you walk around the crystal, you can find regions which look like this. And these one-dimensional features are actually domain walls. And if you zoomed into one of these, here's a domain wall. By the way, you can have many different one-dimensional features. So not all features that look like that are domain walls, but we can check with STM. So if you zoom into one of these, you can do a Fourier transform. And if this region is shifted from this region by a half a unit cell, then you see it in the Fourier transform by a splitting of the Fourier transform peaks. So that's what you can see here. This peak has split into two, and that's because these two regions, the crystal structure is shifted. The splitting of the peak just tells you that you have a shift in the crystal structure, but to see that it's a half unit cell shift, we can do a Fourier analysis and look at the phase, and I'm not going to show you that today. You can, do something crude and track the atoms with your eye. So the white line is the line of atoms on the left-hand side. The red line is the line of atoms on the right-hand side. And you can see that the white lines and the red lines are shifted by half units. So you can find domain walls like this if you search, and then you can go and do spectroscopy on these domain walls. So the blue spectrum is far away from the domain wall, and you see these multiple coherence peaks like I showed you before, and a flat density of states. And if you go to the top of the domain wall and you take a spectrum, you see something really curious. You see you can see the remnants of the superconducting gap, but you see a very flat density of states with a very high density of states inside the gap. So this density of states is very, very non-zero. So you can also check this by, so here's, this is an intensity map. It shows you, this is a line cut in this direction and then in this direction. So if you follow the orange line and you take spectra along this line, you see zero density of states, that's the superconducting gap, and these are the coherence peaks. But then when you get to the domain wall and you take a line cut, you can see that inside the superconducting gap, the density of states is pretty much flat.
This
So
Fourier transform that you're discussing, is this a Fourier transform of the density of states?
No, sorry, I did not show you the Fourier transform at all. So this is an intensity map.
Yes, that I understand.
Of just the spectra, of only the spectra. So I'm taking a spectrum along each point, and instead of actually showing you the spectra, I'm representing the spectra as an intensity map. Mm-hmm. So zero density of states is this dark region here. These coherence peaks would be these yellow lines here. And then this is following this and then following the red arrow. As you go along the domain wall, you can see that inside the gap, you see sort of very flat density of states. So there are no sharp features or no peaks, just this flat density of states. So constant density of states is what we see on the domain wall. So you can ask the question, is this domain wall feature due to the fact that you have some kind of a, this is an actual crystalline domain wall, and perhaps it's a spectroscopic feature, nothing to do with superconductivity. So we've done temperature dependence. And so here, this is, the data I showed you before was at 300 millikelvin. This is at 1.7 Kelvin. You can still see the superconducting gap. It's actually broadened. It's hard to tell one from the other, but you still see this flat density of states at the domain wall. And then when you go above TC is around 14 Kelvin, you can see that the density of states on the domain wall is flat. So this feature has disappeared. And also if you compare the domain wall density of states and the density of states far away at 14 Kelvin, they both look flat and very similar to each other. So this feature is directly associated with superconductivity. This is the phase map that I was telling you about of the Fourier transform. So if you look at the phase of the Fourier transform, then on the left-hand side and the right-hand side, you can see a pi phase shift between these two regions. In any case, so the question is, what does this mean that you have this flat density of states? So to answer that, you can ask, what do you get if there is a pi phase shift? And Fu and Kane did this and showed that what you expect to see is, so this is the superconducting gap, which is shaded. So inside the superconducting gap, you should see helical Majorana states. So these are propagating Majorana states, which means that in this direction along the domain wall, the dispersion looks like this. It's linear. You should see linear dispersion for these Majorana fermions. And across this region, they should be trapped. So they're trapped in this domain, right at the domain wall. So the interesting thing is that if you have a one-dimensional system with a linear dispersion, then what you expect to see is constant density of states. So that's exactly what we see. So we believe that the constant density of states we see inside the superconducting gap comes from helical Majorana modes at the domain wall.
Vidya?
Yes?
Could you just go back one slide from
Sure.
One more? Back to that cartoon of the, right. Okay, now when you first showed not this one, but the one that showed the cartoon of the
Yeah.
that one, right? Okay, right. So when you first showed that slide, I thought that when you were talking about the phase, that you were talking about the macroscopic phase of the superconductor. But now it sounds to me like you're talking about the phase of the lattice shift. Are they
Yes.
related somehow, or?
Yes.
Okay,
Yes.
that's surprising. Tell me about that.
Yes, so it is very surprising. In fact, when we first saw this, you know, we couldn't figure out why these two should be connected to each other. But if you believe Jianping Hu's paper, which is why I talked about this paper earlier, if you believe Jianping Hu's paper, then let me see if I can find it. So what he suggests is that in these nuclides, he suggests that the pairing is such that if you take the full symmetry of the lattice into account, the pairing is such that the top layer selenium atoms and the bottom layer selenium atoms have a pi phase shift in the order parameter, just a local phase shift. And so if you find regions where this is inverted, where the top and the bottom are flipped, which is what we have when we have these domain walls that I showed you, then what you expect is that the superconducting autoparameter should show a pi phase shift on the two sides. So it's a very strange thing, yes. But it is the superconducting autoparameter that I'm talking about. At the end of the day, that's what you need. You need the superconducting autoparameter to have a pi phase shift, not the crystal structure. But in this particular material, it seems like they're related to one another.
And is it also fair to think of this as being a Josephson junction that's operating at this exact funny point where you're pi?
Yeah, if you want to think, sure. Yes, although we're not doing a transport measurement.
Yeah, okay.
And the two, usually you have an insulator, right, between the two sides. Here we have the domain.
Well, okay, well, or I mean, in your cartoon, it looks like you've got a topological insulator, and I'm not sure what that means for a Josephson junction, but.
Yeah, no, I think you can think of it exactly as you would think of a Josephson system, but it's just that you're not doing transport and you don't have any insulator between the two sides.
Yeah.
So the last thing I want to say about this, maybe if I have time, I can talk about the uranium ditelluride briefly. The last thing I want to say about this is, you can ask the question, do you have any other evidence that there's some topological physics here? One thing about a topological edge state or a boundary state is that it's required to span the superconducting gap. And in fact, what should happen for a topological boundary state is that as you change energy, the size of this topological boundary state should increase until it melts into the background. So that's what happens to this boundary state. So these are now not topographies, but DIDV maps. So we are measuring the density of states at different energies and plotting that as a function of position. So here at 0, this is actual data. So when it's dark like this is truly 0 density of states. So at 0 millivolts, which is the Fermi energy, you see no density of states anywhere else except at the domain wall. So this is the domain wall mode. But as you increase energy, this is 250 microvolts, you can see that the width of this feature, the domain wall mode, is increasing. And the superconducting gap size is about 1.5 millivolts. So by the time you get to about 1 millivolt, this domain wall mode has spanned the, it's everywhere and it merges into the background. So this is exactly what you would expect for these topological boundary states. Okay, so in this system, it's interesting. I don't think, I'm not saying that this is smoking gun evidence. There are many questions one could ask, but certainly very intriguing, both the vortex core zero bias bound states, as well as the existence of these propagating states along these domain walls suggests that we actually have Majorana states in the system. And in fact, these domain wall states are helical Majorana modes that were predicted to exist by Fu and Kane. So I can pause here and take questions before I talk about uranium ditelluride if you wish, or I could just skip uranium ditelluride entirely. Jimmy?
Vidya, could I ask a quick question?
Sure.
Okay. I'm wondering if, I guess, yeah, it's more, so I'm wondering, is it clear and or do we need more measurements to tell the difference between, so a normal pi junction, a non-topological pi SNS pi junction would also have, well, not quite the same gapless spectrum, but definitely a suppressed gap.
Yeah.
Right. So, and if there are many channels, the gap could be quite small, similar to. So, is it clear? Can we tell the difference here somehow? Intuitively, it's just that the pi sort of interferes and kills superconductivity naturally.
Correct. I think one thing I would say, you're absolutely right. You could ask if this is a simple destruction of superconductivity.
Mm-hmm.
One thing I would say is this observation is it's sort of suggestive that it's not. In fact, if I just parked myself right at the edge, so if I parked myself at the boundary, which I did earlier, and I took a spectrum, it would look like it would completely flat density of states. But if I park myself here, these states are no longer existent here. So I begin to see only these states and these states and these states. So I see two bumps. And then if I go slightly further out, then I would see the bumps actually move further along as you go further out. So there is some evidence that these are actually propagating states that live on the boundary wall rather than a simple destruction of superconductivity. But I guess one would have to, we also did some, actually I didn't show it here, but in our paper, we've done some calculations to, different kinds of situations where if you have just a simple superconductor without any topology than what you expect to see at the boundary, etc. And very often what you see is you get in-gap states, but those in-gap states can be anywhere inside the superconducting gap, and they're not necessarily spanning the superconducting gap, and they're certainly not necessarily at zero. So I agree. I think one should sort of do more theory, but at least experimentally, there's a lot of evidence that this might not be a simple destruction, but
Sure.
Yeah.
Thank you.
We have another question from YouTube. So again, from Adam W, he's asked, how do you know this boundary effect is associated with the topological insulator underneath instead of just the domain wall itself? And also, couldn't you span the phase space by making a Josephson junction out of this material and varying the phase difference?
Yeah, so people are trying. That's the answer to the second question about the Josephson junction. I don't do that, but my colleagues are trying to do that. About the first question, I'd just like to remind you that this is all happening right at the surface because the material has surface states, and it's the surface states that are getting gapped out. And it's those surface states that are responsible for these propagating Majorana fermions. So everything's happening at the surface, even though the domain wall itself is, we don't know how deep it goes, but at the surface, you have these propagating two-dimensional surface states, which are responding to the presence of the domain wall by creating these Majorana fermions. Your question is exactly what Jay was asking earlier. How do we know that the domain wall is not simply killing superconductivity entirely? So we did also check other kinds of domain walls. And what we find is in this material, as well as another material, which is FESE. And what we find is that in all of the cases that we saw for any kind of one-dimensional defect in this crystal, other than this one, we see in-gap bound states that exist. They look like sharp peaks. I removed those slides, I think. Here's one. So what you would see is that this is a 1D defect that's not a pi phase shift. And you see a nice superconducting gap that goes to 0. It's just that the gap magnitude gets smaller. So that's one thing that happens. And then another thing that could happen is that inside the superconducting gap, we see just sharp peaks in the density of states at various energies in a particle hole symmetric way. So those things happen. And so it's only when you have this pi phase shifted domain wall that we see this peculiar feature, which is the flat density of states. Yeah, that's just an experimental observation. So have I answered your question?
I think so.
Okay.
Okay, I'd like to ask about the DIDV plot that you showed for various biases. We've been coming back to that a number of times.
This one?
Yes, there we go.
Okay.
Now, panel F, which isn't labeled, but I'm assuming is 1.4 millivolts, gives me the impression that the region that is the domain wall, where we started off at lower bias as having an increased DIDV, now looks like it has a decreased. In other words, it looks like it's been inverted.
Yeah, that's because, yeah, that's correct. You're right. And that's you can see it here. That if you park yourself at this energy, then the density of states of, is lower than so the coherence peak is suppressed. So that's what you're seeing. Whereas if you park yourself at this energy, the density of states is higher. So that's exactly correct.
Okay, good.
Yeah. So shall I think I'm out of time. I wanted to talk about uranium ditelluride, but I don't know. Okay, shall I just quickly tell you why this is interesting and then stop? Or shall we call it a day? It's
I think if you have a quick few slides on it, it would be interesting to know, and people that have to leave for lunch can do so, and then at some point we'll transition to a more informal discussion.
Okay, let me just do that. So I'll be very, very quick. Let's say it's 11:02. I won't take more than 5 minutes. I wanted to mention this because it's exciting. It's a different system. We think it might be a triplet, chiral triplet p-wave superconductor, which in theory should have chiral Majorana modes, unlike the proximitized system, which has helical. And by chiral, you immediately see only one branch of these propagating Majorana states at the edges, which means automatically that time reversal symmetry should be broken below TC in this system. So this work was done in collaboration with Sheng Ran and Nick Butch at NIST, and they gave us these very nice single crystals. And so these are the other people involved in this work. The important thing here is that, the material has been known, uranium ditelluride has been known for a long time as a heavy fermion metal. And it was only a couple of years ago that Sheng Ran and Nick Butch actually measured resistivity as a function of temperature below 1.2 Kelvin, and they saw superconductivity. So they made these beautiful crystals. They saw that it was superconducting, and that started this whole a huge amount of excitement, mainly because uranium ditelluride is right at the borderline of being ferromagnetic. It's not ferromagnetic, but it's at the border of being ferromagnetic. And it has a lot of ferromagnetic fluctuations. So it's a prime candidate to realize triplet superconductivity. And in fact, there's a lot of work that's being done by Nick Butch, Jean-Pierre Paglioni, and many other people that shows that this is indeed a triplet superconductor. So for example, I think one of the smoking gun experiments is the night shift, which is flat across TC. I should mention the specific heat also, because the specific heat shows something very interesting. At 0 temperature, it shows a very large residue that indicates that only half the electrons are paired in the system. So this is a big mystery, actually, even today. So both the pressure measurements as well as the high magnetic field measurements, all of these point towards this material being a triplet superconductor. So we wanted to do STM and look for these chiral edge modes. So let me just quickly go through this in a minute. So this is what the topography looks like. When you take a large energy spectrum, you see this feature right at 0 bias. This is actually a signature of a heavy fermion. This is like a Kondo resonance. So this is a very high density of states, very close to the Fermi energy, because of this heavy fermion band that comes up below the coherence temperature. So the interesting thing that we found, and I'll just show you one slide and then I'll stop, is this. So what we found is that if you go to the step edges of this material, you find this strange line shape. So the superconducting gap in the system is it's this dotted line. It's 250 microvolts. So you find that on the step edges, you see this funny feature with a peak that lies inside the superconducting gap. So this peak is about 200 microvolts, and a dip actually on the opposite side, also at 200 microvolts. But the interesting thing is, if you go to the other step edge, then it's flipped. So we checked this on many, many step edges, and what we found is that whether this peak is on the left or the right really depends on whether the normal to the step edge is pointing in this direction or this direction. So this system has a handedness, and so these in-gap states they have a chiral symmetry. And so we did a lot of experiments to show that these in-gap states were a consequence of superconductivity. And in fact, I'm not going to have time to go through all this. All I want to tell you is that the presence of these chiral, these states which are actually sensitive to the direction in a superconductor, that suggests that that this might be a helical or a chiral P wave or F wave superconductor. And that's it. That's all I want to say. So let me just stop here and show you this. And thank you again for your attention.
You get the sad applause, but thank you very much for a wonderful talk. So I think we can, take any more questions that we have now and, slowly evolve towards a more informal discussion.
Can I ask a question?
Sure.
This is Yangzi Zhou. I'm a postdoc here. I'm a theorist working on topological insulator and disorder stuff. So I'm curious about this very last thing you show, this step edge and the hint of chirality. Is there any theory to explain this result?
No. There is no theory.
How can I understand this step edge? Is like you have some termination of your sample and then you do the...
Yes, so you could. So one thing I would say is that we've been thinking of these in terms of Andreev bound states. Like at least that's the mechanism for seeing step edge modes. So you can think of this. So this is, for example, this edge here is an edge where, you know, on the left you have this flat crystal, and then you have a terrace, an extra layer of atoms up here. So this is this step edge is the termination of that extra layer of atoms. Yeah.
Okay, thank you.
Sure.
And does it matter sort of how big of a step it is? Like if it's 1 layer or 2 layer or something like that?
Yeah, so we have, there is some dependence on the height, but we haven't completely pinned that down yet. So for example, you know, here you can see that 45-degree step edges show you a particle hole symmetric feature like this, which is centered right at the Fermi energy, inside the gap, of course. There's some indication that if you double this, then you might go to this scenario, but we haven't confirmed that yet.
I get the impression, that's Charles, you know, that your group performs the you know, experiments on transport, density of states, and so on, and you tend to use samples produced by other researchers.
Sometimes, yes.
So it's just, you know, off the top of your head. Very often in you know, experimental work of this type, there are some particularly gifted growers of crystals or samples. And
Yes.
do you have a comment on any of the you know, particular challenges that such people face?
Oh yes, definitely. I mean, there are lots of challenges, but I can tell you for iron, selenium, tellurium, it's a you know, it's always like this. You first start growing the crystal.
You don't get lunch till you go home.
Sorry. Should I keep talking?
Yes, I think that was Jimmy talking to his child.
Oh,
Yeah, sorry about that.
no problem. So yeah, I mean, for iron, selenium, tellurium, I know that you get all kinds of different qualities. The problem with iron, selenium, tellurium is that you can have ion inclusions, so excess iron, and it's an S-wave superconductor, and iron is a magnetic impurity in FeSCTE. So it basically destroys superconductivity. So we spent 1 year looking at samples that had those ion inclusions, and that data was a complete loss. We couldn't publish any of it. So yeah, there's a lot of challenges. For uranium ditelluride, you know, it's amazing. Nick Butch and Sheng Ran, they made very beautiful single crystals, and in fact, you know, let me just show you what I mean. Yeah, so we did Laue on these single crystals, and for these giant single crystals, they're all in one phase. The whole thing is in one phase. And so these measurements are all done on this particular crystal. You can see a very beautiful specific heat jump. And you can see that this happens around 1.6 Kelvin. And in fact, the superconducting gap measured by STM also disappears around 1.6 Kelvin. So sometimes, you know, the materials are good.
So they're not microcrystallites or something in this.
No,
it looks
they're
like
pretty big.
Almost a homogeneous phase. It's beautiful.
Yeah, this is amazing. Yeah. So I think it's definitely an art to make these kinds of high quality crystals. And yes, we've suffered in the past when we have not gotten this kind of quality.
This is Fred Wellstead. I had a question, actually. I think it was back on slide 43. You had a top view that you could see the domain walls. Ah, there. Yes. Yes. So I had, it looks like there's a couple that are terminating there. where they come up, and I was wondering what that was. And there's
I
also a
don't-
dark patch sort of above that one.
Here, this one?
Yes, for example.
Yeah, so there is something going on here with the crystal. I don't know. And one thing I have to mention is we're only looking at the top layer. And so this thing goes deep. And I don't know what it's doing as you go inside the crystal. I can't tell. This line is also a domain wall of some kind. These are two, probably a grain boundary, actually. Yeah. So if you have a dramatic grain boundary, again, what we find is on step edges and grain boundaries, we often see in-gap states. Sometimes we can find Y junctions where you have 3 domain walls meeting. And at the Y junction, we actually see a zero bias peak. Yeah. So it's really interesting.
So that dark patch sort of right there.
There's a line.
Yeah.
Yeah. So I don't remember. I mean, I don't know what this line is exactly. And I don't even know if any of these is actually this. All I was trying to say here is that for the same size region, sometimes you see domain wall-like features and sometimes you don't. And so if you go searching, you have to go searching and you have to zoom in and take a look. Sometimes we find domain walls that look like this.
I guess the other thing that was noticeable in that slide 43 is some of the walls look, much narrower or much sharper than others. Again, below that dark patch, you see there's, quite a sharp boundary there.
Yeah.
Does that mean it's buried, or what is that? What's the significance of?
No, I mean, on this scale, let's see what this is. What scale is this? This is 40 nanometers. So I have to check 40. Yeah, no, I don't know. This is pretty sharp compared to this. So I actually don't know what this is. I would have to go in and take a look.
Okay.
Yeah.
Thank you.
Sure.